In this video, we're going to talk about inclined planes. Let me tell you what's slowly happening here. We've learned about how to describe motion in one dimension, one direction, right? We've learned the kinematic equations, which relate the position, velocity, acceleration, and time variables. Okay? Now, what about if we had things moving or what about if we involved two directions, two dimensions? So things aren't along the x-axis or the y-axis. Now what happens? That's what we're going to slowly ease our way into. Okay, so in this video I want to talk about something sliding down a ramp. So let's say that you had something like this, and let's say that the ramp had a 30-degree angle, and here's the box. Okay, and let's say that there was a length L down the ramp from where the box was starting. Okay, and so the question is, how long does it take? What's the acceleration? Can we describe the motion of this box sliding down the ramp? All right, and let's assume that the ramp, let's say it's iced over so that there's no friction, there's no resistance to the motion. Okay, so what is going on? Well, we know from discussing gravity, we know that if something was falling straight down, we know that the acceleration would be straight down, and the acceleration would be 9.8 meters per second squared, either plus or minus depending on how you define which side's positive and which side's negative. All right, but this is not going straight down. Okay, so what's up with that? Well, bear with me. So here, let's draw. Here's the gravitational acceleration. It has a length of 9.8, and the way that we're going to calculate the acceleration for this situation is we're going to find the component of that acceleration vector parallel to the surface of the ramp. All right, what does that mean? Well, let me draw a triangle. Remember when we talked about vector components and we had that right triangle that always sneaked in with the vector being the hypotenuse? So here's what's going on. Okay, so what we need to do is we need to find this component. Once we find that component, we're going to use that for the acceleration, not 9.8. Does that make sense? Okay, so we need at least one more angle in that triangle in order to find that component. So let me bring to your attention the 30 degrees. Okay, if that's 30 degrees, can you see that I have another right triangle right here, and this has to be 60 degrees? We have a 30, 60, 90 triangle. Okay, if that is 60 degrees, then this angle right there has to be 30 degrees. Okay, this is a pattern that'll show up again and again. When you draw the vertical and then you draw a line perpendicular to an inclined plane, the angle there will be the same as the angle of the ramp to the horizontal. Okay, so in other words, if I have 30 degrees, a 30-degree inclined plane, that angle between the vertical and the perpendicular to the surface will be 30 degrees. If I had 40 degrees down there, I'd have 40 degrees up there. But both of those angles will be the same. Okay, think about the geometry, and you'll convince yourself that those two angles have to be the same. Okay, now using what we learned about trig and what we learned about vector components, I hope you can see now that this is going to be, we're going to need the sign to get that component. Okay, so if the acceleration had a length g, let me use g instead of writing out 9.8. Well, I guess I could write 9.8. So the length of this is going to be 9.8 sine of 30. Okay, so acceleration, the one that we're going to use for when it's sliding, maybe we should call it a sliding, is 9.8 times the sine of 30, which is equal to, you can punch that into your calculator, you'll get that the sine of 30 is a half, so therefore you get 4.9 meters per second squared. Now, once you've nailed that, Everything else is just like we had before. Things moving in a straight line with a given constant acceleration. So for example, if you wanted to know how long it's going to take to arrive at the bottom, you could use, let's see, what would be something we could use? Well, we know that the delta, the length, we know we can use the kinematic equation. Let's use this one. Remember this one? Delta x v is equal to v naught delta t plus 1/2 a times delta t squared. So along down the ramp, it's going to move a length L. The initial velocity was 0, and so 1/2 a sliding, that's the 4.9 times mystery t squared. So go ahead and solve for t. So 2L divided by 4.9 is equal to t squared. So t is the square root of, and 2L divided by 4.9. If this was a homework problem, maybe I would have given you L. Let's say it was 5 meters. Okay, so then you punch that in. So 2 times 5 divided by 4.9. Okay, and that'll give you something around 1 point something. Okay, 1 point. Let me go ahead and do it for you. 10 divided by 4.9. You get the idea. So the point is, the two-dimensionality comes in when you're finding the component of the acceleration vector in the desired direction. Once you have that, then it reduces. Then the problem is not any more complicated than doing one-dimensional motion. Okay, yes. So that's equal to 1.4 or 1.42, 1.43 seconds, if you want to be fancy. All right, that's incline planes.